Today, we're diving into some of the nerdier aspects of how the Hpc7a is built, and thus how you can best extract performance from it by knowing a few key things. We'll talk about the CPU itself, the memory, and the network architecture. Understanding what we've done in all these areas will help ensure that you're sweating these systems to the greatest extent you can without starting to sound weird. Well, any more weird than is normal for HPC people. Sachs is one of our deeply experienced performance obsessives from the HPC engineering team and helps us keep it real. Let's talk.
This one is, it has 192 physical CPU cores across the whole system, which means it's a 96 core part in there. And as with all the HPC instances here, physical CPU cores and vCPUs is all the same. We're turning off hyperthreads because you don't need that anymore. You can actually run on all those 192 there.
Right, and this is we didn't do anything funny with this box. We just chose a different CPU skew on the Hpc7a compared to the Hpc6a, which had half the number of cores. Right, we essentially just went for processors with twice as many cores per socket when we moved to the 7A. Right?
Exactly, yeah. So new generation, higher frequency, higher number of cores, higher memory bandwidth, all of that. So all of those numbers just went up. There's one real difference here, and that is exactly where you're pointing at right now. And that is, if you look at like L3 cache per instance, memory per instance, and all of that, they all stay same even when the instance sizes get smaller. So if you take less cores, you still get the full instance. So that's something.
That's actually, it's not a complex explanation. We're still, when you choose the smaller instance size with the HPC 7th generation instance families, so Hpc7a, Hpc7g does this too. When you choose smaller instance sizes, you're still getting the whole box. We're just rigging it so that it's got fewer cores enabled, but the ones that are enabled in a correct pattern, so that when you're running stuff on all those cores, you are maximizing your memory bandwidth per core. That's exactly. Really all it is, right? There's nothing much more complicated than that.
No, it's really just we're turning off individual cores, but as these AMD boxes are fairly complicated, the way they're built up with chiplet design and which cache is shared with which cores, there's a possibility to get this wrong, and that would be really bad if you would just leave performance on the table. You figured this out once. Why don't you just turn off the cores for me, and we turn off the right ones?
And it's important because if you do the core enablement incorrectly, or the core disabling incorrectly, however you want to see this, what you could end up with is all of your processors running on one particular chiplet, trying to access memory that's on the far side, and you'll get performance that, in technical terms, we would say that the performance might suck.
It's not magic. So just to make that point clear, if you know exactly what you're doing, and you know, like if you look at LS Topo or whatever, you look at the actual hardware configuration, you can do this on your own.
So this is a shortcut to save your performance from sucking, particularly with codes that there might be commercially licensed codes where you're paying lots of dollars per core to have those licenses. You want to maximize the output you get per core from those licenses. Let's talk about the fact that these boxes also have 2 network rails that we need to worry about. And so from an MPI point of view, this is kind of key, right?
Yeah. So if you look at what we put in there, the number of 300 gigabits per second, that is if you use both rails at the same time. So each of those could give you roughly 150. But you have to use both. Even like on just 2 or 4 cores per instance, it still makes a difference if you actually use both rails. You get better performance, you get better throughput. Actually doing that is not really that hard. So if you look at the lower lines here, Intel MPI 21 8.6 is the first Intel MPI to actually support dual rails on EFA. And you can just enable it by setting IMPI multi-rail equals 1. That's all you have to do.
Okay. And literally, that's it, right?
That's it for Intel MPI. You just set that variable. It will figure out which rail goes with which core. It will do all that under the hood. You don't have to do anything. So what is interesting about this multi-rail is that not only what you would expect to get higher bandwidth when using 2 rails instead of 1, but also you actually get lower latency on things like global communication. So this is like if you do an MPI all reduce or scatter or all to all or anything like that, that actually runs faster.
I mean, that stands to reason because each of the NICs that are inside this box are connected to separate PCI root complexes, each of which are connected back to their separate CPUs.
Exactly.
So it's almost like you've essentially got a series of one socket boxes.
Yeah, exactly. So you go the fast way to each of the NICs, and you can leverage both NICs, of course. Yep, so that will help you. So getting back to the MPIs, as we said, Intel MPI. You set this environment variable, IMPI multi-rail equals 1, and then it will take care of anything. OpenMPI will actually do all of that out of the box. You don't have to do anything. It will identify, I have two NICs. Actually, it will ask libfabric how many NICs are there, and libfabric will say, I found these 2. And then it will just use them and allocate them accordingly and figure out which socket or which CPU should talk to which NIC.
And this is versions of OpenMPI going back quite some time. So folks who are even using older versions of OpenMPI probably don't need to worry about this, right? Right. So the good advice that everybody should be following is if you keep parallel cluster up to date with the latest version, you're obviously going to get all this goodness. But the EFA installer, I guess, even if you haven't been able to keep your parallel cluster up to date, you can actually go and download the latest EFA installer and reinstall it, right, in order to get happiness.
Exactly. Yeah. So the EFA installer, and basically what we mean by using the EFA installer is upgrading libfabric. There is a couple of packages in there, but libfabric is the one that is interesting for this use case. There were some changes in libfabric 1.19 specific to Hpc7a. So if you update that, for example, your MPI startup time should get a little bit faster. There was a shared memory size set, which was assuming smaller core counts. So in older libfabric versions, you have to set this FI, EFA, SHMEM, AV size. That's all done in libfabric 1.19 and going forward. And actually, we are already later, so this is already in there. Just go ahead, use EFA installer by default. The download link will take you to the latest version. Just use that, and you're good.
The other thing to say about the EFA installer, the recent version of the EFA installer, is that it does have a bunch of fixes for shared memory if you're using OpenMPI. And that's interesting. There's a blog post about it. I'll put the blog post link up on the screen as well. The reason that's important, Stephen, is because
this is a huge shared memory machine. Yeah. You have a lot of cores talking to each other on the box without actually leaving it. So there are so things that we usually don't talk about that much. We always do incremental changes to libfabric, which is not only functional but also increasing performance of libfabric and of OpenMPI, because we have teams working on both of those projects.
The blog post is really good because it's a good deep dive into the internals of how, more to the point, how libfabric actually works. Because most of the bottleneck that we discovered at an OpenMPI level was actually coming out of the fact that OpenMPI was using the shared memory, the intranode shared memory model supplied by libfabric. And so we had, our engineers had to dive into libfabric and do some work in there in order to shorten some of those paths. So, but the result was I think it's around about a 10% performance improvement for OpenMPI users, which that's, you know, in your world, that's huge, isn't it?
Yep. Yep.
If you're enjoying these videos, please give us a like and consider subscribing to the channel so that we can keep making more to help you understand how the cloud works and to show you new ways to help all the scientists and engineers around you who use HPC every day to do amazing things. It's what gets us motivated as well. See you next time.